pad? Yeah, great. Okay, so last time we started talking a little bit about, this is the second major area where feedback is critical. The first is electronic amplifiers and electronic systems. And the second is this whole area called automatic control systems or control systems. And in fact, the distinction between the two is not really very precise. So the basic terminology in automatic control is shown in this block diagram. And the basic idea is you have a plant. Plant actually, this goes back about 100 years. And plant actually refers to it's a term in economics, meaning sort of the fixed part of a system. Now, it's the part that's, so you should imagine the plant as being something that's fixed, large, probably expensive, and probably dangerous. So you can think of this as like an aircraft or something like that. So that's the idea behind it. It's the part that you're not going to mess with it. Now this thing is a dynamical system, usually, and you have sensors which actually measure the behavior of the plant, critical parts of it, and you have actuators. And actuators are things which actually affect the behavior of the plant. And all this is very abstract now, but when we look at examples, it'll become pretty clear how this works. So the sensor produces a signal that tells you about something, what's happening in the plant. That signal, called the sensor signal, goes into something, a processor, it's also called a controller or something like that, which processes the sensor signals together with the command signals to produce the actuator signal. The actuator signal tells this actuator what to do. So classical examples would be something like in an electromechanical system, like a positioner. In other words, a system that, for example, moves an XY stage, for example, in building an integrated circuit. There, the plant would be the mechanics of the XY table and probably the motors. The sensors would be all the sensors that tell you exactly where the plate, this table is, right? And then those would produce electronic signals, which would also look at the command signal. The command signal would come from an operator and say, move to the following XY position, and it would compare where it actually was with where it needs to be, and generate the correct signal to the motors to move it to that position. That's all makes it sound very simple. So this is the basic. This is abstract, but here are some examples, and maybe this will make it clearer. So for plants, here would be some. In a CD player, and in fact a careful analysis is that there's, I guess, 4 separate automatic feedback control systems inside a CD player, without which it simply wouldn't work at all. It'd be completely out of the question. So there's actually 4 separate systems in a CD player which rely on feedback control. Another example would be disk drive mechanics. Another perfect example of something that would not work, not even remotely, wouldn't even come close to working without feedback control. Here, what it is you have the little head, and you have this disk that's rotating, and you have to move the head over to find a certain track and that sort of stuff. Once you've actually found the track, then as the thing is rotating, it's supposed to be moving in a completely circular motion, but it's not. Meaning it's moving now, say, things like microns. It's shifting left and right. So it's pretty close to circular, but not quite. And the thing actually has to sort of track these wobbles in the trajectory, which it does. If it didn't do that, it wouldn't work at all. Other examples would be things like control plants would be aircraft or missiles, car suspension, engines. Everything is moving this way now, so which is why no normal person can ever repair a car again. It's all electronic. It's all feedback control. So here's an example there that the number of feedback control systems in a car used to be maybe 1 or 2, and they'd be mechanical. Now the average number for stuff designed right now is like 15, and it's just growing. So everything is going to be done this way. Here's a big example would be a giant rolling mill where you have these giant rollers and hot steel coming under it, and you have these giant hydraulic actuators that can move these rollers up and down, and you're trying to control the thickness of the steel or some other property. It's actually used for, here's an exotic application, is in high-rise buildings now. People are actually using active control for things like seismic and wind disturbances. So you have a giant building which either in the wind or under the action of an earthquake will kind of rotate like this. And they actually have things like giant 400-ton chunks of concrete, giant springs, giant shock absorbers, and huge, huge hydraulic actuators to actually counter the to actually bring the thing back to equilibrium as fast as possible either in high wind or something like that. Here's another one that's completely critical. It's XY stage on a stepper machine for IC lithography. I don't know how many people know what this is or no idea? Yeah. Yeah. What's that? Yeah, so it's you know how it, everyone know about this? This is how you actually make integrated circuits. It basically uses photography, except it's called lithography. And so they print, they reduce these usually 4:1 or something like that, and they print it on this thing. And then what you have is a wafer, which is about this big, or it's getting, I guess, 8 inches now, so it's like that. And what happens is a stepper machine, you put, I don't know, a couple hundred dies on one wafer, and the stepper machine sort of goes chunk, and then it makes an exposure, and then it chunks over, and it kind of goes like wump, 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 like that. The difference is that every time it moves, it's moving on the order of half an inch or an inch or so, and it ends up with an absolute accuracy when it finally, before it makes the exposure, which is unimaginable. It's measured in nanometers, okay? So this would be kind of like you going to a specific place in New York City, but surveyed out probably down to a very, very small number. So that's basically and that's what's happening. You sit there and watch the thing, and it just goes like wump, 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 and it looks like some stupid printing, old-style printing press or whatever, except that the accuracy is unimaginable. This wouldn't work even remotely without feedback stuff. Here's a good example of something that's more abstract, but is feedback control all the same. And that's computer networks are all done this way. So for example, routing and admission and these types of control is all done by feedback control. So for example, you're a router, you have packets coming in, and you have many outgoing links. And you look at the outgoing links, and you have multiple ways to actually route a packet to an IP destination, to a destination. And in fact, what you'll do is your sensors will tell you how congested the different links are in the network, right? Or how much delay there is. That's your sensor. And then you'll think for a while, and you say, okay, I'm going to route this IP packet down this way. I'm going to route it towards that place, and then that's it. So that's feedback control as well. Okay. So associated with each of these and many other examples are sensors, and they vary from extremely complex systems like, here's one, GPS. So Global Positioning System is itself an incredibly sophisticated system, but it's just used as a sensor. Radar altimeter also is also very complicated. It's a sensor. A shaft encoder is a little mechanical device. It'll give you an electrical signal that tells you the angle of a shaft. It might be 8 bits, but it could also be 18 bits and give that pretty accurately. You can have an LVDT will actually tell you on a shaft like this how far, it's a linear variable differential transformer, will actually tell you, for example, how far extended a shaft is for a solenoid or something like that. This would be used for all sorts of positioning stuff. Strain gauge is something that will tell you about very, very small displacements of mechanical things. It goes on and on. Microphones, tachometers, you have pressure and temperature transducers, chemical sensors, and something as stupid as just a micro switch, which tells you whether something has, like in an elevator door, whether in fact it actually fully closed. Okay. These are all sensors. And their job, of course, is to convert something is to actually measure something in the plant and give you usually an electrical signal, but it doesn't have to be. That tells you what it's doing. Actuators, these do the opposite thing. They allow a feedback control or a control system to actually act on a system. So these are sort of they have the opposite types of things. Some are obvious. They're hydraulic. You can have pneumatic actuators, electric motors, solenoids, pumps, heaters. Aircraft control surfaces are, for example, actuators. Voice coil in a loudspeaker is an actuator. You You can have piezoelectric transducers. There's just wide range of actuators. And in some cases, if what's being controlled is fairly abstract, like a computer network, you don't really have an actuator. Nothing physical happens. All that happens is that packets start being routed in a different direction, right? And so, in fact, there you don't really even talk about actuator. Okay. Now, another critical part in this system is the idea that there's disturbances also acting on this. And disturbance is basically something it's usually not directly measured, and it's usually something which also affects the behavior of the plant, but is beyond your control. That's really what it means. And for an airplane, of course, that would be wind gusts. In a building, it could be earthquakes. In something else, it could be external shaking and vibration. For example, in a CD player, it's extremely impressive that you can actually move one at all and have it work. If you learn the actual specifications for how tight this little laser diode and sensor has to track the signal on a CD, and then imagine what happens as you're moving it. It's unbelievable that it actually works. And those are external. That's external vibrations and stuff. In an automobile suspension, it could be road surface variations, and in industrial processes, it could easily be variation in feed material. So for example, if you're rolling steel or making paper, if the material going into a process were absolutely uniform, then you would probably figure out how to do it and then set it there and leave it. But the whole point is that when you're doing, say, paper and pulp, these things can have a variety of you get a different load from somewhere else, different load of paper pulp, and the settings that used to work don't anymore. So these are the idea of disturbances. And then finally, the final component is a control processor. That's this thing. And basically, it's moving now towards just general purpose digital processors. It depends on the application, but it's just moving that direction. So that's what it is. But in the past, it's done by human operators. So you'd actually, in a slow industrial process, you'd have people just sitting there, and they would look at pressures and temperatures, these gauges, and they'd have big wheels down below that would change pump flow, that would change flow rates and change the power to a heater. And they would look at these things and look at them and say, okay, well, I'm going to turn this pump down, and I'm going to turn that heat up a little bit, this kind of thing. So that's a human controller. They can be mechanical, and in fact, I guess mechanical control systems go back a couple of thousand years. They can be electromechanical. That's quite common. Analog ones were widely used starting in the 50s and 60s. And now everything's just moving towards general purpose digital processor or special purpose digital processor if the computing power required is very, very large. So that's the way things are. Okay, so that was all just a whirlwind overview of where this is used. It's used in a lot of places, but we'll jump into a specific example, which is actually a better way to really understand what it does and so on. Let me also emphasize again that there's absolutely nothing new here. Nothing. So in other words, it's going to use just stuff you already know. So this is it's just a huge field of application. Okay. So here's an example. We have a plate, and we want to heat it to a desired temperature, T desired. And we have an electrical heater, which we're going to use to heat it up. So here, the plant is the plate. The actuator is the electrical heater. That's the thing that converts our electrical signal into something that actually affects the temperature of the plate. The controller is a box, some kind of box, could be some electronics or something like that, that reads two things: the command, which is T desired, and also and produces the heater power. So it says that 25 watts or 90 watts should go to this plate. And the output, Y, is the plate temperature, T. So that's what we have. So here's a really simple model, because we're going to start simple. And for us, a really simple model is the following, is that with no power and no disturbance acting on the plate, the temperature of the plate will be at the ambient temperature. So that might be room temperature or something. Okay? How much the plate heats up above or below the ambient temperature depends on the amount of power going to it. Okay, so it's plus alpha times P plus D. P is the power we send to it. That's the power that goes through our electrical heater. And D is the disturbance power acting on it. And you might ask, well, what is that? Well, the disturbance power could be negative, could be positive. For example, if you open a window and bright sunlight shines on the plate, D might be half a watt or something like that. And that's just the thermal power you're injecting into the plate from sunlight. Now, it could also be that somebody opens a window and there's a nice draft, cold draft, going across the plate, which is removing half a joule per second. In that case, D would be minus a half a watt. Okay? So you add that power, that's D, and D is assumed, I mean, normally it's 0. It's just 0. So unless something weird happens, like if there's always sunlight on the plate, we can take that into account. But the point here is it's not, and we don't know what it is. It could be positive, it could be negative. To that we add our power. This is completely in our control because we send a signal to a little power amplifier, which then sends a certain voltage to a heating element, and that's that. So that's totally within our power. That's totally outside our power. And alpha is a gain. It's a thermal resistance. It tells you how many degrees the plate heats up if you put a watt on it. And we're going to make it 1 degree Fahrenheit. We're going to make T ambient 70 degrees, just to make it specific. And D is this thermal. So here's a block diagram showing what we have. Our power comes in. To that we add a disturbance power. That goes to this gain, which relates the power to the plate to its actually the difference from ambient temperature. And then we add the ambient temperature, which is 70, and that gives us T. So this is our block diagram. Okay. So now your job is this. You're going to build a box, and it's going to have a dial on it. And the dial says T desired. You say what temperature you want, and the box will then send out an electrical signal to the heater, which will then heat the plate up, hopefully, to this desired temperature. Okay? Well, so how do you do it? Well, this is not so hard. What you do is you say, well, since you don't know D, could be positive, could be negative, we're going to ignore it. This is time-honored tradition in engineering and science. It's worked very well. If you don't know something, just ignore it, and then move on. And then either it'll come back and make trouble for you, or it won't. That depends on the application. A lot of times it doesn't. So we'll just ignore it, and we'll say, look, the temperature rise you get is just alpha. Alpha is 1, right? So in fact, it's very easy to construct a table that says if the person wants 130 degrees Fahrenheit, we know what power to put in. It's 70 plus, I don't know, what's 60? 60? Yeah, so you need 60 watts or something like that. In other words, this is going to be called an open loop controller. And here it is. I'll put in the power that yields the desired temperature when the ambient temperature is 70, the thermal coefficient is a degree Fahrenheit per watt, and the disturbance is 0. And if you solve those equations, you just get this. It's T desired minus 70 degree Fahrenheit divided by 1 degree Fahrenheit per watt. And we'll assume here, this is stupid, we'll assume that the desired temperature is always positive so that we don't have to inject a negative power here. Now, in fact, you can inject negative powers. So we could have, for example, if instead of a resistive heating element, I had one of these semiconductor heat pumps, then in fact, I can easily command an electrical signal to a little thing that will put out or suck away like negative 3 watts. Okay, no problem with that little Peltier module. Okay, so if we put everything together, it looks like this. Here is our controller. It's right here. It takes input the desired temperature. That comes from a dial on our box. You set the desired temperature. I guess there's supposed to be a minus sign there, right? So it subtracts 70, I think, right? Then it divides by the alpha. That gives us our power. Then the disturbance comes in. We don't know what that is. That's the part we just ignored. It goes through alpha. Then you add T amp back in and you get T. This is our system. And the point is that if everything here, if alpha is 1 and D is 0, this whole thing reduces to this. T desired T. This whole thing reduces to that. That's pretty easy to see. This is 1, so that's just a wire. Then you're subtracting 70 degrees Fahrenheit here and adding it here. So it goes away. And D is 0, so it goes away. And you just get this. And what it says is then well, when you set 135 degrees Fahrenheit here, That will, in fact, be the temperature the plate heats up to. So this is great. And it works perfectly if everything is what you think it is. And so the real interesting part is what happens when you're wrong. So what happens if the ambient temperature isn't 70 degrees Fahrenheit? Or if the thermal resistance is not 1 degree Fahrenheit per watt? Or if there's a disturbance acting on it? And the way we'll analyze that is we'll say, let's look at the temperature error. That's the true temperature minus the desired temperature. Now the temperature error, you can work out the formula for it. You just plug all the stuff in, and it's this. It's alpha minus 1 times T des minus 70 plus Tm minus 70 plus alpha d. And look at the terms. They're very interesting. This term here is 0 when the thermal coefficient of the plate is 1, which is what we assumed it to be. It just goes away because the alpha minus 1 goes away. But if you're wrong, suppose the thermal coefficient is 0.9 or 1.1, okay? Then this is going to contribute a term. This term is also really interesting. It's purely additive. It says that if in fact we base the power, our controller thinks the ambient temperature is 70 degrees Fahrenheit. What if it's 75? Well, of course it's going to do the wrong thing. It's going to send too much power to the plate, obviously, right? Because if the ambient temperature is 75, you have to add less power to the plate to heat it up to the desired temperature. But our controller does not know what the ambient temperature is. It simply assumes it to be 70, and if it's not, you get an error. And finally, you get an error right here from that disturbance. In other words, if somebody does open the window and bright sunlight shines on the plate, the plate is going to get hotter than it should be, and that's reflected right here. Okay? So these are our three terms, and it could simply be that in a certain application, it doesn't matter, that there's nothing wrong with this. This is, in fact, I guess most things work this way. This is just how they work. And the way you would analyze whether or not this is good enough for you is you'd go to someone and you'd say, so how much will the ambient temperature change? And they'll say, well, the truth is that this plate will all pretty much operate in this carefully controlled environment, but I'd say it's going to go from 68 to 72. You go, okay, thanks. That says that this term can be up to 2 degrees. Then you go to somebody else and you say, what kind of range in thermal resistance can we expect for this plate? And you say, well, I don't know, we've been manufacturing for a while, we yank them off the line and we test them, and we find it varies from 0.95 to 1.05. And you go, okay, thanks. And then finally, you go to someone who actually installs these in the field, and you say, well, tell me about the conditions and so on, and it turns out D is small or something. You multiply it out, and then you add it all up, and this is called your error budget. And it's either, if for that application all that matters is that you're within plus minus 5 degrees, and you add up all these error terms, and you're in your error budget, you're done. Okay. All right. Here are some scenarios just to see what happens. So we want a plate temperature of 150 degrees Fahrenheit. Oh, I should mention, this is fun, but actually the numbers aren't made up. This is actually a baked chill plate for semiconductor processing. So just for fun. These aren't, anyway, it's taken from a real example. Actually, these numbers aren't right, but this is right. Okay, so here's some examples. The first example is, the first line is, this is what happens if everything is what you think it is, and the error, of course, is 0 degrees Fahrenheit. If the error weren't 0 degrees, then this would be our controller would be a very stupid design, right? Because it meant that it's something repeatable, right? And we just got it wrong. But in other words, if everything is what we think it is, our error is 0. We're dead on. Now let's try this. What happens if the ambient temperature, it's a little bit cool in the room. It's 65 degrees. Now, everyone here knows what you need now is you need 5 extra watts to heat up the plate. Our controller doesn't know this. So it just sets out whatever power it's supposed to, right, which is, in fact, 80 watts. It sends out 80 watts. 80 watts heats it up 80 degrees above 65. That's 145. Your error is minus 5. You're 5 degrees cool. Okay? Okay, let's look at this. What happens if the ambient temperature is right, the disturbance is 0, but that thermal resistance is actually 0.9. It's 90% of what you thought it was. Again, you have an error. It's minus 0.8 degrees. It's minus 8 degrees Fahrenheit. What if there's a disturbance of 5 watts? Well, you don't know this, so it just heats it up 5 degrees. Okay? And you can try all sorts of combinations here, but this gives you an idea. Now, if you look at these numbers and they do not upset you, that's fine. Okay? But the basic idea of a closed-loop controller, we'll see, is we'll judge it by these numbers, these errors. for these different scenarios. So in a closed loop controller, here's what you do. You add a sensor to measure the plate temperature. I guess this is kind of obvious. Now, by the way, there's lots of other things you could do. You could add a sensor that would measure T ambient. That would actually be a smart thing to do. Let's see, what else do we have here? I don't know. You could put some smart logic in it that after a while would learn alpha. You could do that. These are the types of things you could do. But here's a simple solution, which is just to measure the plate temperature. So to measure the plate temperature, what you do is the following. And this is the essence of all of this automatic feedback control. What you do is you send out a power which is equal to what the power should be if all of your assumptions were right. Okay? This is fine. This is the term we've already looked at. Now to that, we're going to measure the actual temperature. We're going to compare it to the desired temperature. And if everything were as it should be, what would this error be? It'd be 0. This would be 0, right? So what we're going to do is this. We're going to bump the power up or down depending on the error. And let's figure out, we're going to do it in a very simple way. This is called proportional feedback because we're actually modifying the power we send by a term which is proportional to the error. Now, we can figure out what the sign of k ought to be really simply. That's real simple. If the plate is too hot for any reason, that means T minus T desired here is positive. If the plate were too hot, what should you do to the power you're putting into it? You should obviously back off on the power, okay? So you should put in, that's the power you would put in had everything been what you think it is, but evidently not everything is what you think it is because the plate, by sensor measurement, is too hot. Therefore, you back off on it. So that's why this is minus k, where k is positive. Okay? So this is called proportional control. And the interesting thing about this control law, this is actually now called a control law or something like that, is it's very simple. It's also very widely used, this type of idea. And it's very important to understand that it does the right thing. In other words, if the plate is too cold, it increases the power. If it's too hot, it decreases the power. And this constant k is a number which gives you kind of, I don't know how snappy, how aggressive the feedback is. For example, when the thing is 5 degrees Fahrenheit, it basically tells you how much power you modify it by depending on how much the error is. Okay, so in an aggressive controller here, k would be large. And in kind of a mild one, it might be smaller. In other words, if you observe you're too hot, you say, okay, I'll back off on the power a little bit. If k is large, if it's too hot, you back off on the power a lot. Okay, so this is the meaning of k, the proportional gain. It's how reactive the whole the system is to errors. Okay. So here's a block diagram now, and now you can understand why we now have a feedback loop. Here's the controller. This is a block diagram that describes this formula. So this formula is exactly this block diagram. Okay? And it's important to actually look at it and figure out that it actually does what I claim it does. So this here is the open loop controller. That's the open loop controller. Here. There's the plant. This is the controller, like that. Now the feedback controller does this. It takes this desired thing, subtracts the desired temperature from the actual temperature, and forms an error. So that's an error. If everything is okay, E is 0. Okay? But I take E and I multiply by K, and I subtract that from the power. So this term here, this is how much you're going to change your power as a result of temperature errors. That's what this signal is. So this is a feedback loop. You can see that. There's your loop right there. And, of course, anybody here can actually work out. This is a system with, let's see, 3 inputs, T desired, D, and T, and 1 output, T. And you could easily write down a formula for what T is in terms of T desired, D, and T amp. So that's the idea. But the main thing is there's feedback here. Well, we can just solve it. It turns out it's not that hard, like solving feedback equations in general. It's just not hard. So here's what you do. That's the plant. That's the controller. You plug these together. You get E is this. And anyway, when you work it out, you get this. You get E is this expression here divided by 1 plus alpha k. And this is very, very interesting because this numerator expression here, that's exactly what the error, that is precisely what the error is here for the open loop controller. Okay? Divided by 1 plus alpha k. Now that ought to look familiar to you because that's basically 1 plus, and then you say, well, that's the loop gain. That's it. Okay? So in fact, what we just found is that the closed loop error is equal to the open loop error divided by 1 plus alpha k. But that's like the sensitivity of a feedback loop. Well, of course, that's what this is, right? So here are some scenarios using k equals 10. K equals 10 means that if the plate is a degree Fahrenheit too cool, I'm going to bump my power up 10 watts. Okay? Now, if you want to think about that, that's really an overreaction factor of about 10 to 1. That's what it is, right? Everybody understand that? In other words, if what it says is if the plate is too hot by 1 degree Fahrenheit, I will back the power off 10 watts. Okay? Now, the truth is to really get it right, you should back the power off 1 watt. Okay? But why does it actually works? Because if I back it off 10 watts, the plate will cool off 10 degrees, and now I'll be, instead of 1 degree hot, I'll be 9 degrees cool. Okay? But that means I should be putting in some positive power, and anyway, so this is all very complicated. But it all settles out into an equilibrium, and in the equilibrium, in fact, what happens is you're off by open loop error divided by 1 plus alpha k. So if you were to compare these errors, here they are. Okay, if everything is what you think it is, the closed loop system works no differently, no better, no worse than the open loop system. But now start comparing these numbers. They're all divided by a number that's around 10. But that's around the loop gain here, right? So these are spectacular, these improvements. So basically what it says, and it's also very, very interesting to get a real physical feeling for what happens here and why does this work. For example, the plate is sitting there. Everything is what you think it is. It's sitting there. It's 150 degrees Fahrenheit. 80 watts, which is the correct power, is going to the plate. Somebody turns off the air conditioning in the building, and the temperature rises to 75 degrees. Okay? It's 5 degrees warmer, and so if the power to the controller just stayed at what it, thinking it's the ambient temperature is 70, what would happen is the whole thing would heat up and be 5 degrees hotter. The controller would realize this and back way off on the power. Anyway, this eventually settles out, and the result is that the controller backs off almost the correct amount being 5 watts to compensate for the increase in ambient temperature. And the net result is small errors like this. Actually, we'll see pretty soon that there's a simple variation on this where these errors will actually be driven to 0, just 0. And in fact, many which is also a very interesting fact. Okay, so what's interesting about this is, anyway, that the closed loop controller handles changes in ambient temperature and thermal resistance and disturbances much better than the open loop controller. And the improvement is precisely the sensitivity. So actually, there's another reason this example is good. The other reason the example is good is because when you study feedback, we're going to study very simple, stylized feedback block diagrams. Very simple things. In fact, we're going to do that next. It's going to look like that. And that's it. Okay. The truth is that in any application, even the simplest, it never, ever looks just like that when you look at the details. Never. So here's an incredibly simple, stupid thing. It really looks like that. And so real automatic control systems have these horrendous, complicated block diagrams, at which point what you have to do is you just have to analyze it. Okay? You won't be able to just plug in the formulas. You'll analyze it, but then hopefully what will happen is you're going to start recognizing things. You're going to say, oh, that's the loop gain. That's the sensitivity, and so on and so forth. So that's the other reason this example is good, is even though it's simple, it's not stylized like these things are. Okay, so we'll look at feedback. That was all just sort of cultural background, and there's a question. Why does it what? Well, actually, if you just solve these equations, if you set k to equal 1, right, which would be kind of, it would be a good, rationale, right? You say if the thing is a degree hot, you should, well, let's explain it. suppose that plate is a degree hot, and we take K equals 1, which would seem to be the right thing to do, because K equals 1 says back off on the power 1 watt for every degree Fahrenheit the plate is hot. Great. So you back off a watt. Okay? Now the problem is, if that were the end of the story, if it were a two-step controller where you measure and then you change the temperature and power and hold it there, that's exactly the right thing to do. Here's what happens though. As you reduce the power 1 watt, okay? Well, the plate cools off now, 1 watt, okay? And now you say, well, what's the error? Right? There's no error now. So the temperature now says, the controller now says, no error, no problem, I'll go back to the open loop control, and it increases the power again, right? So what's happening, it's this feedback thing. It's kind of, it keeps adjusting it and all that sort of stuff, so that's why. That's the idea. We'll see it from here. If it were not continually adjusting, if it made one adjustment and quit, you would set K equals 1. That's what you would do. Okay. So let's look at it. Here's a stylized, a pretty much standard stylized diagram for feedback control. It's not unlike the feedback block diagram we looked at in the feedback block diagram that we looked at for circuit and other areas. Except instead of having a feedback thing here, we have C here. And the symbols are pretty standard. For example, P might stand for plant, and C for controller, or it could mean compensator, it could mean all sorts of things. This is it. So this is the picture, and these are the traditional terms. E is the error, that's just like in the other case. R, instead of U, is again a traditional term. R means the reference, and it's usually a command. It's the reference, and so the idea here is you want E small. R is probably what you want Y to be. Y is the output of this thing, and U is traditionally the input to the plant. So that's a bit different. This is standard. I mean, these are sort of standard these are different fields here, sort of electronic amplifiers, and so that's why neither the block diagram nor the symbols are consistent. But actually what you'll find out pretty soon is that you can make a simple little table that will relate these things, the various formulas and the signals, and that's what you can do. And actually the really good news is that since nothing in practice looks like this, or like the amplifier one, the really awful truth is that every time you actually really encounter something like this, you have to figure it out yourself. So really the only important thing here is to be seeing patterns, of stuff. And then, so that way when you actually work out the details of your personal feedback system, right, then you'll start seeing formulas and patterns, and you'll say, oh, hey, wait, I recognize that. That's probably the loop gain. And you'll go and look at it, and you'll trace some loop through your system, and you'll say, oh, yeah, it is. What do you know? Okay. So this is the picture here. Now, you can also do things like add disturbances. For example, you can add a disturbance there, you can add a disturbance there, you can add a disturbance there, and give them all sorts of names. For example, you might add this, and this could be wind gusts. Okay? You could add something here, and this would be, in fact, sensor noise. This could be your gyroscope, your inertial navigation system error would be added there. Because this is really where you are. And this signal is where your inertial navigation gyroscope assembly tells you are. Hopefully they're very close. But if they're not exactly close, you call the difference your inertial navigation error. So it could be much more complicated than this. But this is the basic idea. And the usual goal here is that Y should be close to R. That's the idea, that R is a command, for example, a heading or an altitude in an airplane, and Y is the actual heading or altitude. And if everything is working right, you want E, the error, it's suggested by the name, of course, to be 0. That's the idea. Okay? So what we'll do is, at first, we'll consider the static and linear case. And that means that all these things are numbers. They're not, this is the simplest system, just like we did with feedback in general. And what you do is, now it's just too boring to even work it out, but you work out, for example, what Y is as a function of R by eliminating E and U. And here's what you find. You find that the closed loop gain from R to Y is PC over 1 plus PC, and you can write that as 1 minus S. Okay? S is 1 over 1 plus PC. Note that it's basically the same as the other one. It's 1 over 1 plus AF. Okay? So again, that's called the sensitivity. PC over 1 plus PC is called the closed loop input-output gain. And the closed loop gain from R to E, which is also a very interesting thing, is S. Okay? So what that says, it's very interesting. It says in this system here, the closed loop gain from R to E tells you what, for a given size R, what kind of error you're going to get. So if that number, the closed loop gain from R to E, is 0.05, that has great significance. It says that when you put in 3 here, the error here will be 0.05 times that. In other words, the error will be 5% of the command signal. That's of the required signal. That's the idea. And you can work out the various details. For example, if you take t and you work out what the change in t is divided by t, the logarithmic change or fractional change here, and you relate that to the change in plant, you get precisely S again. So it's basically exactly the same. Same story. If you get large loop gain, and it can be positive or negative, doesn't make any difference at all here, then it says that implies S is small, and that implies that t is about 1. T is the transfer, is the gain from R to Y. And it says if that's about 1, it says that Y is about equal to R. That's exactly what we want. It says E is small. The error is small. The I/O gain also is insensitive to changes in plant gain. That comes from here. Okay? For example, if you have 20 decibels of loop gain, it says that T is about 1 within about 10%. And you have Y as R within about 10%. So the tracking error is roughly 10%. And in fact, this is about the loop gain we had in the example we just looked at. It was about 20 decibels of loop gain. Okay? So this is sort of the idea. This is very, very important in all the applications, I mean, especially this here, right? Because, for example, if everything were working open loop, we'd be in deep, deep, deep trouble because a good example would be to take a control surface on an airplane. How far a solenoid extends or a motor or how a hydraulic system works is critically dependent on temperature. And if you're, once you're at 30,000 feet or something like that, just to use this example, I'm not sure how we got onto this example. But are you bored with it? Should we move on to another one? I don't know. It's just something big and dangerous and so on. Anyway, I can assure you that things like that the actual gain of a little electrohydraulic actuator is going to change greatly over the temperature range. So you need the loop gain there to make sure that when a pilot moves a stick or something like that, you're going to get an equal number of degrees of deflection when it's warm and on the ground and at cruising altitude. There's a question.
What is the distinction between your closed loop gain and then just your normal loop gain?
People would refer, people refer to P as the open loop. They've talked about that as the open loop gain of the system.
Okay. Is that the same thing as just normal loop gain?
Your loop gain here would be PC, right? And then the closed loop gain is from R to Y, is PC over 1 plus PC. Okay? So there's actually minor variations. For example, in the other system, it's A over 1 plus AF. It's not AF over 1 plus AF. So, but of course, the block diagram is different, so you kind of expect that. But the basic ideas are the same. I guess that's the critically important part. So let's see, open loop equivalent system. This is a way to compare a feedback system with something that did the same thing but open loop. And let's see how that works. Here's a closed loop system, and the gain from here to here is PC over 1 plus PC. That's the gain from here to here. Well, it's not really fair to compare that to P for a variety of reasons, right? If you really want to compare this closed loop system, you want to compare it to an open loop equivalent system, which has a gain C over 1 plus PC, like this, because then the gain from here to here is the same. It's this. Okay? So this is referred to as the open loop equivalent system. And the difference is this thing has no feedback. Okay? But actually there's a very big difference here. This here, the difference between this system and this, actually, as the block diagrams are drawn, there is no difference. This is the same as that. Period. Because you multiply it out, you divide it, you get exactly the same thing. However, if I were to change this P 10%, this system is not the same as that. Because when I change P 10%, this one changes 10%, but this one doesn't. Because this is really a model of P, which is probably contained in a couple of lines, in a section of code in the control processor. And it doesn't change. Okay? If I were to add a disturbance here, right, as opposed to here, very different things would happen. Here, the disturbance just adds to the output. Here, the disturbance adds to the output, but it also comes around and goes back through here again. So who knows what's going to happen? So these things, as I've drawn them, are exactly the same, right? But if you start messing with things in here, different things happen. And let's look at what those are. Let's do changes in P. So if you do changes in P, if we work out, here's the closed loop system. You have C and P plus delta P. And you simply work out what the change in closed loop gain is from here to here. And it turns out to be this expression here. Okay? If you look at the open loop equivalent system, you just do the analysis here. This is pretty simple. You get this. Okay? And if you work out, if you then relate the two, which is the idea is to compare the open loop and the closed loop equivalent one, assuming that delta P times C is pretty small. Basically what you get is the change in closed loop gain is equal to the change of the open loop system times S, the sensitivity. And that's for a small change in the plant. You get that. So again, this is to be expected. It says basically that this system handles changes in P if S is small, if the loop gain is large, far more gracefully than the open loop equivalent system. You can work out the response to input and output disturbances. Here, if you work out what it is, and actually I believe you have, I think you have. We made you do this at some point, except it didn't mean anything to you then. So here you work out the, maybe we did something like this on the midterm, I think even. I can't remember. Yeah, okay, I think so. So if you simply work out what the effect of these two disturbances is on Y, you get this expression, okay? If you look at the open loop equivalent system, you get the same thing, except that it's P dn, or here, I guess it's on the next page here. If you work the same thing out here, it's very simple. What happens is d out just adds, and d in gets multiplied by P, and you get this. And what happens now is that the closed loop response to disturbances is exactly equal to the open loop response, but multiplied by the sensitivity. And so what we have then, of course, is if you have large loop gain, you get small sensitivity, and then the effect of the disturbances is small. And we'll look at one more thing, and that's sensor noise. And actually, it's very important to consider this one, because it's the one that goes the other way. Here it is. If you have a sensor noise here, that's adding something in here, and you work out what the effect on Y is, it's minus PC over 1 plus PC times desensitivity. Now, in an open loop equivalent system, you have a sensor, and you add the sensor noise, and then what do you do with the sensor signal in an open loop system? Nothing, because that's what an open loop system is. You don't use it. So what's the effect on Y in this open loop system of this signal desense? 0, because for what? You don't use a sensor. That's another way to say it, of course. If you had a sensor, you don't use the signal. And so, which is really interesting, it says, here's a case. Sensor noise is actually something where the feedback system is worse than the open loop system. The reason is pretty obvious. Here, any error injected here, it goes through, and it will definitely have an effect on Y. It might have a large effect, small effect, we don't know, but it's going to have one. Whereas in an open loop system, of course, you don't have that. So this is pretty obvious if you have a temperature controller. Here's a classic example. You have a temperature controller, and you have a thermocouple or something that measures the temperature, and the thermocouple gets confused or wrong. The open loop one works just fine because it doesn't have a thermocouple to go wrong. The closed loop one, if you start getting if it starts giving you the wrong sensor signal, it's going to start making corrections to the power and all that kind of stuff based on a totally wrong signal. And of course, it's going to have an effect that's going to induce an error. So that's a disadvantage. Okay, so the summary is basically this. is that once again, this curious number, 1 over 1 plus AF, here in this context it's 1 over 1 plus PC, kept coming up over and over again. And it was a number that told you what the benefits of feedback were, if it's small. If you have L large here, I mean, it could be not AF. I guess this should even be PC. I don't even think, I mean, that's probably, it's just probably copied from the last lecture. Sorry. If you have PC here, if that's large, then S is small, and you get all these benefits of feedback. And here are some disadvantages of feedback control. One is basically the cost of the sensor, because you need to have one. Another is reliability, because if your sensor fails and your system is critically dependent on a sensor, you're in some trouble. And finally, the sensor noise affects output. And we're going to see other disadvantages of feedback. But for the moment, in a static analysis, there are a lot of advantages, and that's these. Okay, so we'll quit here, and then I guess Wednesday we'll do dynamic analysis of feedback.